Water looks simple, but the molecular structure underneath is already telling you why life exists at all. What looks like ordinary liquid is really a master key that unlocks every biological function. And the failures of modern water bodies spread from the point where that key breaks. Water is not healthy anymore. Some people see water as backdrop scenery or commodity plumbing. Other people see it as a chemical formula memorized in high school. But I see something more structural. I see the hidden molecular machine that makes resilience possible. And I see the exact thresholds where that machine fails. Through a forensic lens, water is not simple H2O. It is a precisely calibrated molecular architecture, and every collapse in a modern water body is ultimately a failure of that architecture under stress. That one bent angle already explains our existence. Look at the water molecule itself. Two hydrogen atoms bonded to one oxygen atom at a precise angle of 104.5 degrees. That V shape creates an uneven distribution of electrical charge across the molecule. The oxygen side pulls electrons slightly closer, becoming faintly negative. The hydrogen side becomes faintly positive. This polarity turns water into the most powerful solvent on Earth. It can pry apart and dissolve more substances than any other liquid because its charged ends attract and surround other molecules like tiny magnets. Nutrients move through a cell because water molecules pull them into solution. Waste leaves a body because water molecules escort it out. The blood that carries oxygen through your tissues is possible only because water can hold those oxygen molecules in suspension. But that polar charge is just the entry symptom. The deeper mechanism is what happens when billions of those bent molecules come together. Each molecule can form weak magnetic-like bonds with its neighbors. The slightly positive hydrogen on one molecule attracts the slightly negative oxygen on another. These bonds are called hydrogen bonds, and they last for only a few trillionths of a second before breaking and reforming in a constant molecular dance. But in those fleeting moments, they create collective behaviors that no other liquid on Earth can replicate. Hydrogen bonds are why water has an abnormally high boiling point for such a small molecule. They are why liquid water can absorb immense amounts of heat before its own temperature rises, stabilizing climates and protecting cells from thermal shock. They are why evaporating water requires massive energy to break those bonds, which is what makes sweating an effective cooling system. And they are why water expands when it freezes instead of contracting like almost every other substance. When water molecules slow down enough to freeze, hydrogen bonds lock them into a rigid hexagonal lattice with more empty space between molecules than liquid water has. Ice becomes less dense than the liquid around it. It floats. That floating layer insulates the liquid world below, allowing aquatic life to survive winter. Without hydrogen bonds, ice would sink. Lakes and oceans would freeze from the bottom up. Entire ecosystems would be crushed season after season until only surface life remained. But here is what that means when you apply it to a degraded water body. Every time we heat a river with thermal pollution, we are not just raising the temperature. We are forcing hydrogen bonds to break more frequently and stay broken longer. Warm water holds its molecular structure more loosely. Dissolved oxygen, which aquatic life depends on to breathe, escapes more easily from warm water because there are fewer stable hydrogen bonds to hold those gas molecules in place. A river that has been heated by industrial discharge is a river where the molecular machinery of oxygenation has been physically dismantled. The fish die not because the water looks dirty, but because the water has lost its capacity to hold the oxygen they need. That capacity loss is written into the physics of the hydrogen bond. And the harder part is that this molecular logic scales. Water reaches its maximum density at 4 degrees Celsius. As surface water cools in autumn, it becomes heavier and sinks, forcing warmer, oxygen-depleted water from the bottom to rise. This seasonal turnover redistributes oxygen to the deep layers and nutrients to the surface. It is a hydraulic lung. Lakes and reservoirs depend on this mixing to stay oxygenated year-round. But when we add dense saltwater pollution or nutrient-heavy runoff to a freshwater system, we create a layer at the bottom that is too heavy to mix. The salt wedge sinks and stays there. The seasonal turnover stops. Oxygen never reaches the bottom. Nutrients never reach the top. The lake stratifies into a two-layer failure system. The surface looks alive. The bottom becomes a dead zone. What looks like calm water is really a collapsed convection system, and the molecular density difference that should drive mixing has been weaponized into a barrier that prevents it. Internal loading begins when the oxygen runs out. In an oxygenated lake, phosphorus and toxins bind to particles and stay locked in the sediment. But when bottom waters lose oxygen, a chemical shift occurs. Iron changes from a form that traps phosphorus to a form that releases it. The lake's own sediment begins leaking buried phosphorus and toxins back into the water column, feeding algae blooms that consume even more oxygen when they die and decompose. The system eats itself. This feedback loop is not a metaphor. It is a direct consequence of water's molecular behavior under low oxygen conditions. The hydrogen bonds that normally stabilize dissolved oxygen are not forming frequently enough. The result is a self-reinforcing cascade where oxygen depletion triggers nutrient release, which triggers more algae growth, which consumes more oxygen, which releases more nutrients. The molecular machinery that should regulate the system has become the machinery that accelerates its collapse. Now look at water's relationship with proteins. Every enzyme, every structural molecule, every chemical messenger in a living cell is a protein that must fold into a precise three-dimensional shape to function. Water molecules do not just surround proteins, they actively push and pull on them, guiding the folding process. Hydrophobic parts of the protein, the parts that repel water, collapse inward to escape contact with water molecules. Hydrophilic parts, the parts that attract water, spread outward to maximize contact. This hydrophobic force is the primary driver of protein folding. Without water's molecular choreography, proteins would not fold. Enzymes would not function. Cells would not exist. Life depends on water's ability to sculpt molecular complexity out of chemical chaos. But that dependency becomes a vulnerability when water chemistry shifts. Microplastics are hydrophobic at a molecular level. They repel water and attract oily industrial toxins like a magnetic sponge. When microplastics enter an aquatic system, they do not just float inert. They concentrate pollutants to levels hundreds or thousands of times higher than the surrounding water. When a fish ingests that microplastic particle, it is not just swallowing plastic. It is swallowing a toxic payload that the plastic's hydrophobic surface has been collecting and concentrating for months. The same molecular force that allows proteins to fold is now being exploited by synthetic materials to concentrate poisons. The molecular logic has not changed. The input has. To understand the full scope of this system, we have to look at water's thermal capacity. Water can absorb more heat per gram than almost any other substance because breaking hydrogen bonds requires energy. Every time a water molecule heats up, some of that energy goes into breaking and reforming hydrogen bonds rather than raising the temperature. This makes water an incredibly effective heat buffer. Oceans stabilize global climates by absorbing solar energy during the day and releasing it at night. Cells rely on water's thermal inertia to prevent temperature spikes that would denature proteins and rupture membranes. But when we dump thermal pollution into a river or lake, we are not just adding heat. We are forcing the system to spend its thermal buffering capacity on waste heat instead of environmental stability. The molecular bonds that should stabilize the ecosystem's internal temperature are being consumed by industrial cooling systems. The water's ability to protect life from thermal shock degrades in direct proportion to the heat load we impose. The fish that die in a thermally polluted river are dying because the water has lost its capacity to buffer temperature at the molecular level. And this is exactly what that symptom means when you see a water body that still looks clear but can no longer support the species it used to. The molecular infrastructure is failing. Surface tension is another expression of hydrogen bonding. Water molecules at the surface are pulled inward by hydrogen bonds from below, but not outward from above because there is no water there. This imbalance creates a film strong enough for insects to walk on. It allows water to climb through the narrow vessels of plants in defiance of gravity. Cohesion between water molecules and adhesion to vessel walls combine to pull water hundreds of feet up the trunk of a giant tree. But surface tension also controls how pollutants disperse. When surfactants from detergents or industrial runoff enter a water body, they disrupt hydrogen bonding at the surface. Surface tension collapses. Oils and toxins that would normally bead up and float now spread into thin films that cover vastly larger areas. A single drop of oil can spread across several square meters when surface tension fails. Aquatic insects that depend on surface tension to breathe or move lose their footing. The molecular skin that held the air-water interface intact has been chemically dissolved. The system also shows that water's incompressibility creates structural resilience. Water molecules are packed so tightly by hydrogen bonds that they resist compression. This near incompressibility allows water to act as a hydrostatic skeleton for soft-bodied organisms like jellyfish and worms. It allows blood pressure to transmit force through arteries. It allows plant cells to maintain turgor pressure that keeps stems upright. But incompressibility also means that water transmits shock efficiently. When a boat propeller spins at high speed, water molecules cannot rearrange fast enough to move out of the way. The surface effectively becomes solid. Marine mammals caught in propeller strikes are not just cut, they are struck by a surface that has temporarily lost its liquid behavior because molecular rearrangement cannot keep pace with mechanical force. The same property that gives water its structural strength also makes it capable of traumatic mechanical damage under high-speed conditions. Finally, we have to look at the isotopic fingerprint. Not all water molecules are identical. Some contain deuterium, a heavier isotope of hydrogen. The ratio of normal hydrogen to deuterium varies slightly depending on where the water originated. Evaporation preferentially removes lighter molecules, leaving heavier isotopes behind. Precipitation carries isotopic signatures that differ by latitude, altitude, and season. Scientists use these isotopic ratios to trace water's origin through the global water cycle. But deuterium is not just a tracer. In high enough concentrations, it is toxic. Replacing normal hydrogen with deuterium slows down the speed of chemical reactions because heavier atoms vibrate more slowly. If you replaced all the water in a living cell with pure heavy water, the cell's biochemical machinery would slow down until it could no longer sustain life. The molecular speed of hydrogen bonding is calibrated to the mass of normal hydrogen. Change that mass, and the entire system fails. This reveals the final diagnostic layer. Water is not just a passive medium. It is an active participant in every chemical reaction, every structural process, and every energy transfer that makes life possible. Its molecular properties are not arbitrary. They are precisely tuned. The 104.5 degree bond angle, the partial charges that create polarity, the hydrogen bonds that last only picoseconds but collectively govern everything from climate stability to protein folding. These are not incidental features, they are load-bearing elements of a molecular architecture that life has spent billions of years depending on. And that is what makes the degradation of modern water bodies so forensically legible. Every thermal pollution event is a forced breakage of hydrogen bonds. Every salinity intrusion is a density disruption that prevents seasonal mixing. Every microplastic particle is a hydrophobic toxin concentrator. Every nutrient pulse is a trigger for oxygen-consuming blooms. Every surfactant spill is a surface tension collapse. These are not vague environmental harms. They are specific, diagnosable failures of water's molecular machinery. The water body that looks calm on the surface, but no longer supports the species it used to, is not mysteriously sick. It is experiencing a documented loss of molecular function. You, the viewer, should watch for the signs that the molecular system is under strain. Watch for temperature shifts that exceed seasonal norms, because those shifts directly predict oxygen loss. Watch for salt wedges and stratification, because those predict mixing failure. Watch for algae blooms, because those predict internal loading and oxygen depletion. Watch for species loss that starts with sensitive organisms, because those are the canaries signaling that molecular conditions have crossed a threshold. What looks like ecological complexity is really molecular physics, expressing itself at scale. The diagnosis is not speculative, it is measurable. Water is not dead yet, but that is the point. The molecular machinery that makes water capable of supporting life is not binary. It degrades incrementally. A river that has lost 10% of its oxygen-holding capacity still looks like a river. A lake that is stratified into a two-layer system still reflects sunlight. The surface symptoms lag behind the molecular failures, which is why the degradation is so easy to miss until it is far advanced. The crisis is in a substance that still looks like water, but no longer functions like water at the molecular level. Now you know what to watch the next time you see it. You know that the bent angle and the hydrogen bond and the picosecond pulse are not abstract chemistry. They are the load-bearing infrastructure of life. You know that every failure we see in a degraded water body is traceable to a specific breakdown in that infrastructure. And you know that the molecular discovery that explains our existence is the same discovery that diagnoses our losses. Thanks for watching. I appreciate you. If this helps sharpen how you see water, consider subscribing. Tell me which water body to cover next. I will keep building the case files.